Okay. Good morning, everybody. I hope everyone's having a wonderful day. I want to welcome you to CS 340, Advanced Data Structures and Algorithm Analysis. Sorry, not analysis, algorithm design. See, I'm so excited I can't even get the name of the course right. Either way, we're going to be seeing a lot of analysis in this class, hence why I say that. My name is Dr. Daniel Page, but you could just call me Dan or Daniel. I'm not too terribly picky. My email is daniel.page@uregina.ca, and I'll mention these things in a moment. First, I want to welcome you to the class and hope you're excited as I am about this. So in this lecture, I'll be first talking about the course outline and just going through just some details I want to highlight from that. I encourage you to review the course outline. It is on your courses. But I'll be going over there to to get over to where we need for the course outline. Let me just migrate over there. So I just need to move the chat and everything over this way, just so in case anybody has any questions while we're doing things, because sometimes these things sort of, it's sort of the fun of having multiple screens going on. Okay, let me just move on over. Okay. Okie doke. Let's move on over here. First, can everybody see my PDF here of the course outline? Okay, good. Excellent. Good. So anyways, so I'm just going to briefly go through this, just so there's some things I want to highlight. So obviously you're here, so you found how to get to the Zoom call. So we're all good. So just, it's worth noting my office hours are Mondays and Fridays at 8:30 till 10. And on Wednesdays, I'll have office hours from 11:30 till 1. So I'll have plenty of time available for students if they have any questions or they want to stop by. Everybody's welcome to my office hours. Don't be shy. If you have a question or you just want to stop by and pick my brain for a little bit, it's encouraged. So just worth noting, prerequisite for this class is CS 210. So you need to have taken and completed CS 210 to be in this class. So just worth noting a couple of things. There is no required textbook for this class. Instead, I'll have some optional reference texts. So should you find my lectures insufficient or you really just want to find another perspective on this, I would encourage you to seek out one of these books. Below on the first page here, I make some remarks about what books are appropriate for what parts of the course. You'll find that the first book generally will give you a good idea of this one by Weiss here. This one will generally give you a flavor of a lot of the things I'll talk about in this class. But the other two, like a particular introduction to algorithms, I have it over there. Let me go grab it. If you find yourself really wanting an excellent text on, like if you ever find yourself, say if you're doing a co-op, or you really just want a really big, nice reference text, this book, Introduction to Algorithms, is a nice collection. If you find yourself really just wanting a book with a whole bunch of data structures, a whole bunch of algorithms, and a lot of the analytical things we'll see, for example, in this class, or in this book. It's a really good book if you find yourself interested in algorithms. It's a little bit more mathematically oriented, but you'll find that if you come out of this class, this book will feel a lot more comfortable for someone like say you. Another book that I should also point out is one called Algorithm Design. It looks like this. Sorry, it's a little bright there. Let me get that. There we go. This text is quite good if you're looking for a text mostly just focused on algorithm design itself, hence its name, by Kleinberg and Tardos. You'll find that in this book, that I find it's good for the sake of, for a lot of the later stuff we're going to talk about in this course, specifically about algorithm design techniques. So you'll find that I like the way the authors talk about how they design the algorithms. They kind of go through the rationale of how you come up with the ideas. So it's one I can also recommend, but like I said, none of these are required. This course will be generally self-contained. So you don't have to go and buy a book. Don't worry. So just as a gist of a couple other things. So first, are there any questions about that? Hopefully I'm 100% clear. So don't go out and, you don't have to go out and buy a book. Don't worry about that. But if you feel like you really just want that reference text, so for example, if you really just want to find another book that like, hey, look, I want to do some little bit more reading about this, these are 3 I can recommend. Okay, I think we're all good. So let me just move on ahead. So in this class, you'll find this course is going to be broken up to about 5 parts. So the first is really going to be analysis of algorithms. So I'm going to be stitching together concepts that you've seen in CS 210 with things I'm going to be introducing in this class. So I'll be reminding you of things like what data structures are, what an algorithm is. Sorry, I'm getting so excited here. And we'll be moving into talking more about how you analyze algorithms. Some of these things you may have seen in a previous course like 210, but I'll be kind of building up another layer on top of your understanding from 210. So I'll be kind of building up this more formal way of talking about analysis of algorithms. And on top of that, we'll talk about Big O. How many of you have never seen Big O before? Has anybody never seen Big O before? Or we're all familiar with what Big O is? Because I'm sure if you've taken 210, you've probably seen Big O notation before. Yep. See, that's what I thought. Okay, good. Yeah, so I'll be talking about Big O notation. We'll be doing more formal stuff with Big O and some other asymptotic notations. We'll be writing out some proofs and things like that. So you'll find this course will be much more formal than 210 was. And I'll talk about properties. But either way, if you've forgotten or if it's been a while, I'll be recovering that. So don't worry. So I'll be generally talking about some examples and do some analysis. So I'll be focusing mostly on searching and sorting problems to do this because these are problems that you may be familiar with from previous courses. In the second component of this course, I'll be talking about data structure. So I'll basically be picking up from 210 and I'll be moving right over to talking about some more data structures. So I'll be focusing on a little bit about an so-called amortized analysis. So this is a special kind of worst case analysis where instead of looking at the running time given just one operation, like if I insert an entry into a binary search tree, I look at, say, for example, multiple operations that occur and how the worst case behavior gets affected by multiple operations as just to one. So we'll talk about that a little bit. I'll give the example of how you resize an array. You may have heard of some practical tips about resizing arrays when they get full or they get too big. I'll be trying to justify in theoretical terms how using amortized analysis why some of the tips you may have been hearing about in previous courses actually are true. In addition, I'll be talking about priority queues. So I'll be talking about so-called heaps and mergeable heaps, and I'll show you some other implementations of priority queues. We'll also talk about dictionaries, and I'll be using the example of splay trees. I'm pretty sure in 210 you've probably seen a lot of different trees. You may have seen binary search trees before, so I'll be just assuming you know what a binary search tree is. Has anybody never seen what an AVL tree is by any odd chance? I'm pretty sure in 210 AVL trees tend to get covered. But if anybody hasn't, just let me know. Don't be shy, because I will just assume you know what an AVL tree is sometimes. Yeah, it should be, but yeah. Okay, good. But yeah, depending on time, I'll try to get as many data structures as I can. That's generally what I'm getting at here. Third, we'll move into talking about graph theoretic algorithms. So I'll talk about what a graph is. But yeah, if we need to talk about anything involving a data structure, I will try to give you some refresher on it. So don't worry. I won't just like cold turkey you on it. But when it comes to this, I'll be talking about what a graph is, some major terminology. Then I'll talk about graph traversal. So I'll talk about so-called depth first search versus breadth first search. I'll talk about some applications of what you could do with graphs. So for example, if you want to find a route from 2 points in a space, or if you want to represent a route like a map, like if you have 2 physical locations that are represented as spots on a map, I could tell you how you can compute a shortest path from one to the other. We'll be talking about some examples of problems like this. And so I'll be showing a lot of fun things you could do with graphs. Then beyond that, I'll be moving into algorithm design techniques. So here I'll be showing you a lot of kind of what I would consider kind of the bread and butter techniques that people, if you want to know about algorithm design, these are kind of the standard techniques that I want you to be familiar with. So we talk about greedy algorithms, divide and conquer, and so-called dynamic programming. And depending on how much time, I'll talk about backtracking and branch and bound, which are pretty handy for problems where you have large so-called search spaces and you need to search for a solution, but they get really big really fast. But the fifth one, this is probably the one that if you talk to a student about this kind of class, you'll find that the algorithms and data structures will in fact be a very important portion of this class. But the final part, I will say that if you come out of this class, and one thing that hopefully will blow your mind is part 5 of this class. So I'll be talking about computational complexity theory and talk about complexity classes. And I'll be trying to show you how, when we talk about problems actually interrelate with one another. And once you realize that you can actually convert one problem to another problem, and you can do this efficiently, then it opens up a giant gateway of how you can solve all sorts of different problems. So we'll be talking about that, and also some limitations of computation and what possible ways, and that's likely how I'll close the class, is ways we can possibly deal with the so-called intractability. So question in the chat. For graph traverse, do you cover A star when object is moving bigger than the size of the graph? Square. I won't be talking about A star, but A star is another one of these graph traversal approaches that is quite similar to the ones I'll be talking about in this course. Just A star sort of has an extra step on top of it with the way it formalizes things. But yeah, no, I won't be talking about A star though in this course. There's a lot of stuff in this class. I'm really excited about it. But anyways, that's just a general gist of what this class is going to be about. There's a lot of stuff for this class. So just as a remark, as you are here, this is in fact a synchronously delivered class. So we'll be meeting here at the scheduled time. And it's worth noting that if, say, you do miss class or you want to refer back to a previous lecture, I have a YouTube channel I'll be posting these lectures at. It's worth noting, just for the sake of privacy, that nothing that is being in the Zoom call is going to be recorded except for what you're seeing right now on my screen, and only my audio. So don't worry too much about, like, if you're really worried about, oh yeah, no, well, what if I have a question? Is it going to be in the video? It's not going to be in the video, so don't worry. If you're really shy and you worry about asking a question, remember, don't be shy about asking questions. It's okay to be wrong. Believe me, that's one of the most important mechanisms when you're asking a question, is remembering that if, say, you ask a question, there's sometimes a chance that somebody else is also curious about the same thing. And if, say, you throw out a question out there, remember, if you ask it, I'll only have 2 options. Either I'll tell you I don't know, or I'll try my best to answer it, or I'll have a clear and exact answer for you. So technically, I guess it's 3 or more, but we'll go with that. Like I mentioned, there are going to be written notes that I'll be posting after the lectures. So these are going to be prepared as I'm doing the course. So I mostly would want to post them after the lecture in case I catch any last little bits of things. But keep in mind that in this class, I strongly encourage you to take notes. So I'll be working from the board over here. I'll be doing some fun demonstrations too. You'll find that writing notes will help you learn this material a lot easier. So I encourage you to do that. But for the sake of accessibility, I will be making lecture notes, and these are going to be available. So for example, if, say, I skip ahead a little bit and say you weren't able to write everything I had on the board, you can always refer back to the notes. Or if you just want to read a little bit more about things, I may throw some extra things in the notes. But when it comes to the course material itself, I'll only care about what's in the lectures, unless I tell you otherwise, okay? Office hours, they're going to be on Zoom. I had office hours earlier today. Just come hang out. You can always ask me questions. I'm pretty sure we all got an idea of what we should expect from Zoom. Just when you enter a call, make sure you mute your mic unless you want to chat. Like I said, don't be shy about asking questions. Asking questions is an important part of learning. I find that it's one of these things that if, say, you really aren't sure about something, you can either ask it right away, or you can wait till later and you can always ask me. I usually like to hang around lecture afterwards a little bit. So if you have any questions after, unless I have to go somewhere right away, which I will probably let you know if I had to, I'm happy to answer a couple questions here or there. If anybody has any questions, whether it be about an assignment or things like that, I'm happy to do that. And like, I think everybody sort of got a hook of what to do with Zoom. So there's going to be 5 assignments in this class. I have the dates. This is a tentative breakdown of the schedule. So for example, next week I'll be posting assignment 1 on Labor Day. Keep in mind there are no classes on Labor Day, but I just want to give it to you in case you want to just take a peek at it. You'll have a few weeks to finish that. I generally like to space out the assignments so you'll have plenty of time to finish them. So you'll find that when I give you an assignment, you shouldn't necessarily need all the time to complete it, but it's a good idea to get started as soon as you can. So if you see a problem and you're like, oh, I already know the stuff to do that problem, I encourage you to give it a shot, okay? So other than that, there is a midterm. This will be conducted on your courses using the quiz module. So that being said, I'm going to be using ProctorTrack to my to my reluctance. But that being said, there is going to be an onboarding quiz. It's on your courses on the course website right now. I would like you to complete that onboarding quiz as soon as possible. Why? Because for each one of your classes, you have to do one of these onboarding quizzes to sync up the stuff for ProctorTrack. So this midterm, you'll probably look at the grades and be like, oh, well, why is it that the midterm's only worth 10%? It's because, well, one, I don't like to hurt. I'm not out to get you. Okay. I see the midterm as an opportunity to get yourself prepared for the final exam so you can see the kinds of questions I can ask you. So that's why I don't like using very heavy-fisted midterms, but you should not take it lightly. So I just want to make sure that you see it more as an opportunity to see what the final exam is going to be like in terms of the kind of questions I can ask you. But generally the flavor when it comes to assignments overall, you'll find that most of these assignments are all going to be written. So there's going to be next to no programming in this class, except for in the first assignment. So you'll find that you'll spend a lot of time thinking about things as opposed to implementing things on a computer. That's what's going to kind of contrast, say, 210 from this class, is you'll find we're going to really formalize a lot of ideas. But yeah, the final exam scheduled at a date and a time. It's in the course outline here. I'll recommend you check that out. Just general policy, you can take a look at this. It's not too bad. We're in a third-year class. I'm pretty sure you guys know the good gist of this stuff. I don't want to waste too much of your time, okay? So assignments, just keep in mind that I have a specific format I would like your assignments in. So for example, I want to have a title page. You'll be submitting your assignments as PDF files on your courses. So just keep that in mind. So if you're not sure how to create PDF files, you can always send an email and ask me, but I'm pretty sure most of you will be fine. But don't be shy. Remember, I'm not out here to like point at you and be like, oh, you over there. Don't worry. I'm here to help, okay? So the biggest thing I need to point out is that some professors like to be flexible with deadlines. I am not the kind of person. I think that if I give you a deadline, it is strict. So unless there's some extreme situation or accommodation needed, I do not provide extensions on assignments because I give plenty of time already to finish them. Hopefully that's understandable. So that being said, just don't like email me the night before the assignment is due and say, Dad, I need more time to do the assignment. I will not have much sympathy for a scenario like that. I have plenty of time I've given you for the assignment, so I'll just expect that. So let's see. What time of day the deadline should we expect the assignment to be due? Okay, so now if you'll see the assignments, what will happen is you'll see that it's actually by the end of the day. So it'll be like 11:59 p.m. of that day. So you'll have till the end of the day, but it's worth noting, and this is like worth noting because I know that some students sometimes that crunch is very real. I will leave the submission open till about 7:30 in the morning. And I will not penalize you if you submit within that window at all. So on paper, it's 11:59, but because nobody's really going to ever look at it until the morning, I have the submission open until later into the wee hours. So if you find yourself really just needing that extra time, really just to check over your things, that's not an issue. So hopefully that clarifies that. So you'll see quite quickly that I'm pretty flexible around the deadline, but not the date itself. So it'll be right around, so you'll have like 11:59 plus the night of. So if you need a little bit more time, it's okay. But nothing beyond that. This is mostly because I want to make sure that everything stays on a regular schedule for everybody so that your assignments can get marked on time and you can get your marks much quicker. Plus, I like to post solutions for all my assignments. So I like to do that as quick as I can. So one other thing, if say you get an assignment back and you're not sure why you lost a mark or something like that, I'll likely have TAs marking the assignments. So I'll make sure that the TAs let you know who marked the assignment. So if you have an issue, you can contact the TA. Likewise, if there's any issue beyond that, you can always bug me about it. But go to the TA first. But it has to be done within the first 2 weeks of getting the mark back. That's just generally to keep things on track. Other than that, I have a question in the chat about the midterm. Yes, the midterm is proctored, so it'll be using Proctor Track. So the final exam and the midterm are using Proctor Track. To my reluctance, but that is just the nature of the beast here, at least when it comes to this kind of class. So that's talking about proctoring. So like I said, we're using Proctor Track for this course when it comes to the midterm and the final exam. Just be aware of the requirements. So just check out this link and read this message. I put a message there from the university about this. The midterm, there is a scheduled time for it. Make sure you're there and you can complete it at that time. There are no makeup tests, okay? So if you can't make it for that time and you don't arrange an accommodation with me and you say the time elapses after this midterm, I will not be able to accommodate anything. So you have to let me know. So when it comes to cheat sheets, I'm not actually sure at this time. I will give it some more thought at this time. I like to make sure that students up front know my expectations. So I'll let you know if you're going to have a cheat sheet. I'll make it clear as black and white. I think for this kind of class, I think it might make sense. However, at the same time, you'll find that a lot of the stuff I'll be doing in this class, it's going to be very much based on what's up here, not so much what you can regurgitate. But so we'll see. We'll see. I have to think about that one. I appreciate the question. Generally, I don't allow cheat sheets, but because this course is online and you will be doing probably a lot of rough work anyways, it almost be indistinguishable from my end. But I'll definitely give it some thought. If you do have and want say, if you're curious or you want to give me some background about cheat sheets, you can always send me an email about this if you have any concerns. But for now, just presume there are no cheat sheets. So just assume that at this time, okay? So academic integrity is something I want to talk about. It's something really important with me because I care a lot about standards. So you probably have had this spiel given to you numerous times at this point, but I have to do it because it's important. So I will not accept any form of cheating in this class. So what is cheating exactly? Well, for example, on a midterm or a final, that could be copying down answers to things, using additional resources, because these could be closed book tests, for example. And you say if you have a binder open, you're reading up notes, obviously that's cheating, right? But another form, of course, is plagiarism. And that's a very important one with this class because, one, the assignments in this class are designed to both test your understanding of the material, but also to get you thinking so that you could take the ideas that we see in class and apply them so that you could see how we use the ideas and you could see how they yield results. So very often in this class, if, for example, you didn't actually do your own work, you'd be basically not only cheating in terms of plagiarism, but you'd also be cheating yourself from learning about the material yourself, because the assignments are being designed so that they apply what you see in class. So hopefully that's clear to everybody. So when it comes to cheating, you don't want to be in the scenario where you're hanging out with your buddy, whether it be on Zoom or Discord or some other thing like that, and be like, hey, look, can you show me your answer for this problem? Do not do that. Just don't do it. Here's kind of a thing that can be really helpful for you. However, I find very often it's helpful to talk about your work together with other people if you're curious about something. Like, so for example, if you wanted to discuss a problem on the assignment with somebody else, For example, you may use a whiteboard or some notes, and you may talk to each other about things. The thing I recommend is if you ever talk to somebody about the assignment, do not leave that discussion at all with anything written down. So only talk about things. Don't write anything down and bring it to each other, because each assignment is an individual effort in this class. They're not meant to be collaborative efforts. Hopefully that's clear for everybody. So if you're say working on an assignment and you're like talking to a classmate about this, just don't write anything down. Just ask about you could talk about the things, but just don't write anything down if you're planning to like leave that discussion and think this is going to be my work, because you have to produce your own assignment. It's an individual effort. Other than that, don't look up answers online. I do tend to craft my assignment questions to try to wean this, but at the same time, it's also worth noting that I am pretty aware of resources where things are. And if I find out that you used a resource online, I will go to the fullest extent of using academic dishonesty policies on you. Hopefully that's clear, because you'll be cheating yourself out of learning about the things in this class and applying them for yourself. I hate it sounds like I'm berating anybody. I apologize if it comes off like that, but I think this is pretty clear for everybody. Hopefully this is all good for everybody. Can you give me a thumbs up? Just let me know. But yeah, you'll find very much with this class, you'll be spending a lot of time thinking about things and pulling out pieces of paper or working on your tablet and thinking about ideas to do things. That's what you'll find a lot with the assignments in this class. Tutoring, of course, similar issue here. If you have a tutor, don't make your tutor do your homework for you. Do not do that. I used to do tutoring for a number of years. It's a no-no. Don't encourage your tutor to do your homework for you. That is a big no-no for a tutor to do in the first place. You could use a tutor, of course, to ask questions about things, but don't make it about the assignment. Just ask about concepts. That's usually a good rule of thumb. If you have an incident where you require accommodation, whether it be through a disability or other means of that nature, do contact the Center for Student Accessibility. I'm happy to accommodate given certain circumstances or certain parameters of this class. So other than that, I already mentioned the class recording policy. Other than that, don't make your own recordings of the lecture unless you ask me first. So just keep that in mind. And also remember, I am going to post everything I'm doing right now is going to go on YouTube. So don't worry, this will go up. So if you feel the need to record something, don't worry. If you want to hear what I'm talking about in the class, don't worry, it's going to go on YouTube. And other circumstances, say for an accommodation, if say a student requests that they need to hear the audio for the whole lecture, I'm welcome and open to that. But there are certain parameters that the university has for example, you have to destroy the recordings after the term and things like that. But it makes things a lot more tricky, okay? So other than that, like I said, you can talk about the assignments and concepts all you like in this class. Just remember, your work is your own. As I mentioned already, start the assignments early if you can. Do them in chunks. Just like, okay, I'm going to do problem 1 this day, or I'm going to do part A of this problem this day. Try to do that for yourself, especially remotely. It's so easy to lose track of things. Other than that, for emails, try to keep them concise. If you have a question, make sure it isn't already on the course website. It saves a little bit of time for everybody. And obviously, if you can, talk to me, pick at my brain, talk to your fellow students if you're looking to have a discussion. It's always a great thing to do. Are there any questions about the course outline? That's generally all I have to say about the course outline. But yeah, give it a look over. There's some things I didn't discuss here explicitly. Are we all good? Give me a thumbs up. Okay, I think we're good. If you ever just want to ask me later, you're more than happy to ask me later. Okay, so let me... has anybody started a Discord server? If anybody wants me to set up a Discord server, I can set up a Discord server if anybody wants that. Or if you amongst yourselves want to do that, I'm also okay with that. Just make sure you keep me in the loop on that, okay? Okay. Because I do use Discord. As funny as it sounds. Okay, so let me just move on over here. Okay, so let me just move over here. Okay, I think I got everything there. Okay, just want to make sure I got one last thing. I just got to move the chat over. It's one of the fun things of having having a couple of screens going at the same time. Generally, you'll find I'll hang out in this lecture area. So I won't be bouncing back and forth unless it's to discuss things like assignments. Okay, so let me get started. So I think we're good to go to start up things. So, okay, so I'm going to shift gears now. We're going to start talking about the material in this class. So I want to give you a flavor of some core concepts we're going to see in this course. First, can everybody see me out here on the lecturing space? I like to lovingly call this area the learning zone. Okay, good. Okay, good. Okay, so we're going to get started here. So the first thing we're really going to do is I'm going to kind of lay out some core concepts that some of them you maybe are already familiar with. If not, I'm going to sort of give you a primer on them, just so that we kind of have an overall idea of the framework for which we're going to talk about things in this class. Because even though the course is called Advanced Data Structures and Algorithm Design, this course is really about problem solving. That's one thing that in this class that you'll find that I'll talk a lot about problems in this class. So that will be kind of the central focus of this class. So I'm just going to talk a little bit about some main concepts. So some main concepts. So the first thing I really want to talk about is that a core part of computer science is problem solving. So that being said, we need some working definition of a problem. So I'm going to give you a rough framework that a lot of algorithms researchers tend to use. So I'm going to define what a problem is for our purposes. So it's going to be a question or statement that requires solving. I know this is going to seem really redundant, a statement that requires solving, but you got to remember, in this class, I'm going to start pinning things down beyond just a rough idea of a wiggly idea of something. I'm going to start trying to pin things down for you. There are ways to pin these things down even further and more exactly, but that's beyond this class. That requires solving. So here's the big part of this, and I'm going to draw a picture that's going to really kind of blow your mind, okay? So I'm first going to write down a sentence, and then I'll explain this. So a computational problem is an infinite, I'll put this in parentheses because it doesn't necessarily have to be infinite, but an infinite collection of possible problem instances. So there's going to be two parts to a problem instance that I want you to be aware of. Each problem instance which oftentimes will get abbreviated as instance. So if I say, oh, this is an instance of that problem, I mean a problem instance. Of a problem has inputs. So sometimes this is called the input instance. And upon being solved, has a solution. So the big idea I really want you to get it, and it's going to really boil down to this picture. And I'll kind of connect everything together. So imagine I give you a problem, and I call it capital Pi, like this. Now, every problem we're going to talk about is going to be consisting of so-called problem instances. So they're just going to be little dots here. And each one of these is, in fact, a problem instance. So for example, if I could call it x, I'll say x is in problem pi. So this means set. This is set theoretic for in. So you just read this as in. So if I talk about a problem and I define it in exact terms for you, I have to consider every problem instance of the problem. So a question I have for you is, if I want to solve the problem, if I claim to you I have a wonderful algorithm that could solve the problem, what does that mean in this context? So if I give you any x, does that mean it has to produce correct output, as in it produces a solution every single time? Yes or no? Yes. So that means that in this framework, it's very exact. And you'll notice that there is no wiggle room for me to say like, okay, that one, the answer could be wrong. This could be wrong. This, all of them actually have to be that if I feed it to an algorithm, it produces correct output. So I'm going to be formalizing this and drawing a fun picture to connect up this all together. So let me make one remark. I have to make this one very important remark. It's going to sort of creep up later on in this class, but I have to acknowledge it. So let's wiggle on over here. So we're going to talk about the idea of input size. Now, just because I need to make sure I capture everything together, I'm just going to talk briefly about input size. I have a little bit more detail in the notes, but I'm going to talk about input size just for a little bit here. Just so it's clear to everybody that this is one of these other core pieces. You may have seen input size before, or sometimes it's called input length in 210, but I'm going to just formalize it a little bit further. So I'll say, let me just write a little lower. So each problem instance x for problem pi has its own size. Has its own size. So you might ask, what exactly is the size of an input? Like how big is that? Well, if you think about it in terms of like an actual computer, it should make sense. Like it should be how much information it requires me to represent it, right? And that's what input size is. So formally, so this is the fancy definition of input size. Input size, and often it's denoted with these bars like this. So you might ask why bars like this. It's because you may know this as like for cardinality or length of a string, for example. It's because on a very fundamental level, like you could represent any encoding of bits as a string. Hence, this is why they use this notation very often. Okay. So formally, input size is determined by how many bits. Now, I must stress that I'm not going to write it down here. It's in the notes. That it doesn't necessarily have to be bits. It could be any reasonable encoding scheme. So if you want to use ternary, you can. Is the only one that actually is considered is not one of these reasonable encoding schemes is so-called unary. That's where so in binary you have zeros and ones. Unary is just ticks. That's an example of a so-called unreasonable encoding scheme. This will come up towards the end of this class. It'll be somewhat relevant then. So that's why I'm not writing anything like that yet. So how many bits are required I was just getting excited there. Are required to encode X. Seems pretty nice, so I'll just give you some examples. So for example, you may already know some examples of reasonable encoding reasonable considerations of the input size. So for example, if I'm sorting an array, A of length n. If I sort an array of length n, what would be the input size here? I want you to think about it. It depends on the sizes of each one of the elements in the array, right? But you know, an array, really when you create it, it's based on some type, and those types all are of fixed numbers of bits, right? So like 32-bit integers, for example, or something like that. So if I have n of them, you should expect the input size to be a reasonable measurement of the input size would just be n. Is n. So that's just one example of input size. As just a remark, just a quick one, if, for example, we had it where the numbers could be arbitrary in their size. So for example, if I just presume that the numbers could be as big as you want, no matter how many bits, it may be relevant. Say it involves a parameter that is outside of the machine I'm using. So for example, it may have it where the numbers could be arbitrarily big. They're not some fixed word size on a computer. This input size could change, right? But in our circumstances, this is what it's going to look like. I just feel like I need to acknowledge that. If you have any questions about that or anything, anytime, feel free to ask me. I sometimes like to throw these things out there just to give you an idea that there do exist circumstances where you can have all these other ideas pop up. That's why input size is important. So just as another example, to traverse a binary search tree, it can be the number of nodes. The number of nodes in the tree. So that's another example. Seems pretty natural, right? One I'm going to throw in here just for the sake of throwing you through a loop is determining I'm getting excited already. Determining if a number is prime. Now, you might ask, okay, well, what would the input size be here? Is it just going to be like a constant or something because it's only one number? Well, in this kind of problem, the number actually really matters. It's actually an important part of the problem, right? Remember, there's an infinite number of these. So I'm going to be considering a number, and I ask, is it prime or not? So if I want to measure the size of the input, it's actually the number of bits to represent that number. Because in this problem, it's not about the number of numbers, like how many numbers you have, or a number of elements you have. It's actually about this number itself. That's it. It's a problem involving numbers. So this will matter if you want to be a little bit more careful. So is the number, getting excited again, is the number of bits to represent, my represent sort of melted in the microwave, to represent the number. So just as a remark, I'll wrap things up on this. So just because I mentioned it earlier, I'll just say it here. We will assume the numbers, so this is outside of these examples, we will assume the numbers are encoded using some fixed number of bits. So when we do this, we'll be assuming that we're really going to be measuring input size by the number of elements, typically. And this is typically reasonable for most problems we're going to consider in this class. When we have a problem that involves numbers, like numbers where the number itself could appear in the running time of an algorithm, that becomes where we actually have to start getting really careful. But for this problem, for most of our stuff, it's going to be built right into the machine model we're going to use for analyzing algorithms. So it's very intuitive. Just like an actual computer, you would have like ints that are encoded with a certain number of bits. Just like if I have a char, it uses a certain number of bits. That's what we're going to assume in this class. It's intrinsic to the model that we're going to use for analyzing algorithms. So hopefully that's clear to everybody. So are there any other questions before I stop for today? Are we all good? I think we're all good, I think. I don't see any questions. Oh, I'll answer that one after the lecture, okay? If there aren't any questions, when we come back, I'll be talking about some examples of problems, and I'll be connecting up what I described here, what I said earlier, with problems and algorithms. I'll draw you a nice picture that connects everything together, and then we'll start talking about algorithm analysis. So, that being said, hope you have a wonderful day. I'll see you later. So, let me just